Hello friends, in this video I'd like to solve the following problem from the Romanian International Mathematical Olympiad Team Selection Test 1993, problem number 1. We wish to prove that the sequence of imaginary parts of product 1 plus I, 2 plus I, 3 plus I, and so on, n plus I, has infinitely many positive terms and infinitely many negative terms, where n goes through positive integers. So, in other words, our sequence depends on n, is the index, and we are taking further and further products, and we wish to show that infinitely many terms of this sequence have imaginary part positive, infinitely many have negative imaginary part. Okay, it's a nice problem concerned with complex numbers. Here are my hints. I have a bunch of hints and terminology. First, recall this very basic fact that every complex number which is not zero can be written as z equals r times e to the power I times phi, where r is positive number, it's a radius between origin and this point, and phi is some angle between 0 and 2 pi. And moreover, this representation is unique, and that allows us to define the argument of a complex number z to be exactly this angle phi. So argument, don't get it wrong, argument of a complex number is the angle. So in other words, when we have complex plane, we have some point, here is our r, and here is our angle phi, also known as the argument. Also, when we are multiplying complex numbers, the argument of this product is congruent to the sum of arguments, modulo 2 pi. So, in other words, when you multiply complex numbers, you are adding arguments of it. Okay, then notice that imaginary part is 0 when we are above OX axis, and above OX axis every point has an argument between 0 and pi, and below OX axis we have arguments between pi and 2 pi. And moreover, notice that we can normalize our numbers. If z is not 0, then the argument of z is the same as the argument of z over the modulus of z. This has an advantage because this number has the modulus of 1. It's also rather intuitive because when we have some number, let's say here we have our unit circle. Well, if I normalize this number to lie in this unit circle, the angle stays the same, obviously. Then, another fact, if x is greater than 0 and y is a real number, then the argument of x plus I times y can be found by using arctangent function. It's arctangent of y over x. And you should also prove the following two claims. One is rather trivial, that the limit as k goes to infinity of arctangent of 1 over k is 0, but the series as k goes from 1 to infinity of arctangents of 1 over k actually diverges. And to prove this second claim, notice that the harmonic series diverges, and you should use the limit comparison test. And after all of that, think geometrically. Think what these facts mean geometrically. My claims, my connection with argument with arctangent, and so on. When you do connect the dots, you should be able to explain that our theorem must be true, that we must have infinitely many positive and negative terms in our sequence. So give this problem a try, and I will see you in a minute. Okay, so maybe I will start, not to interrupt my reasoning later, I will start with proving my lemma, my lemmata. Claim number 1, well, limit as k goes to infinity of arc tangent of 1 over k is 0. Well, there is nothing to prove here because argument 1 over k, it goes to 0, and we know that arctangent of 0 is 0. So there is nothing to be proven. We can triumphantly write our end of proof sign, but there was no proof. Okay. Claim number 2, much more interesting. Claim number 2, I actually claim that the series as k goes from 1 to infinity of arc tangent of 1 over k actually diverges. How can we prove it? Proof. Notice that, well, every term of this sequence is obviously positive. Moreover, 1 over k itself is also positive. And what's the limit? What's the limit as k goes to infinity of arc tangent of 1 over k over 1 over k? Well, we can change our variable. Instead of k, let's put 1 over x. So here we have x, and here we have x. So 1 over x goes to plus infinity. So x goes to 0 from the right-hand side, but doesn't really matter. Maybe let's write it in yellow. X goes to 0. And here we have arc tangent of x over x. And now we have 0 over 0. We can use de L'Hopital's rule, for example. And by the de L'Hopital's rule, it's the same as taking derivative of numerator and denominator. Well, in the numerator I will have 1 over 1 plus x squared, and in the denominator I have just 1, so it's just 1. So these two sequences are asymptotic to each other. Maybe I will write, here we are using de L'Hopital's rule by de L'Hopital's rule. And notice, moreover, since harmonic series is divergent, well-known fact, by the asymptotic test, or maybe it's better called by the limit comparison test, our series of arctangents diverges as well. And that closes the proof of my second lemma, of my second claim. Okay, now let's tackle our problem. We are dealing with 1 plus I, 2 plus I, 3 plus I, and so on, n plus I. Now, I wish to find the argument of this sequence. Well, notice that this number is obviously not 0, so the argument is well defined. Okay. First of all, I will normalize my series. I will normalize my product by dividing each term by its modulus. And if I do that, it's the same, argument stays the same. The modulus of the first term is square root of 2. Then we have 2 plus I. The modulus is 5. 3 plus I. Modulus of 10. 9 plus 1, yes, and so on and so on. Finally, n plus I, square root of n squared plus 1. I'm just using the Pythagorean theorem to find the modulus. I'm taking real part squared plus imaginary part squared. Okay. Now, let's call these numbers, or maybe, yes, let's call these numbers. This is Z1, Z2, Z3, Zn. This whole number, yes? Okay, and now I wish to find the argument of each of these numbers, because I know that argument of of my product is congruent to sum of arguments. So it's congruent to argument of 1 plus I over square root of 2 plus the argument of 2 plus I over square root of 5, argument of 3 plus I over square root of 10, and so on. Finally, we have the argument of n plus I square root of n squared plus 1. Now, what's the argument of each of these numbers? Well, we can take y, because both coordinates are positive. X coordinate is positive, that's really what matters. So, and I'm taking my congruence, of course, modulo 2 pi. And so that means that here, the first argument is just arctangent of y over x. Y is 1, x is 1. So it's arctangent of 1. Here we have arctangent. Y is 1, x is 2, so of 1/2. Then we'll have arctangent of 1/3, and so on and so on. Finally, arctangent of 1 over n, of course, modulo 2 pi. So in other words, we know that argument of z k equals arctangent of 1 over k. We can write it as well. But for every k, positive integer k, the argument of zk is arctangent of 1 over k. 1 over k. Very well. Now the crucial step is to observe some things. Our numbers, each of our number, maybe let's also write it, after normalization, our numbers zk have the modulus of 1. So they lie on a unit circle. So let's draw our complex plane. Here we have our imaginary part, real part, and here let's say we have our unit circle, horrible unit circle. Much better. Okay, and now our numbers are on the unit circle. Each time we are moving along the unit circle because each multiplication adds some angle. So we are moving along our unit circle. Now, notice two things. This journey will have no end because we know that our series of arctangents of 1 over k, it diverges. So we'll make as many revolutions around the origin, as many as infinitely many, in fact. So maybe let's write it that so product z1, z2, and so on, zn is, so maybe when computing z1, z2, and so on, zn, we are actually rotating number one about the origin by angle. By what angle? By angle series going from sum going from k equals 1 to n of arctangent of 1 over k. Moreover, by claim number one, each multiplication adds smaller and smaller angles, smaller and smaller angle, because we know that these arguments, these numbers go to 0. So each multiplication, we are making smaller and smaller changes of angle. Very important. By claim number 2, furthermore, by claim number 2, we will make infinitely many revolutions about the origin. Yes, because each time we are adding some angle, by claim number 2, we have proven that the series of arctangents diverges. So this angle increases, it has no end. So our points will go infinitely many times around the unit circle. And steps will be smaller and smaller. So geometrically, it should now be clear that each quadrant will be visited infinitely many times. Yes, there is no possibility to skip some quadrant. For example, it's not possible that we are right here and we somehow skip this entire quadrant, because that would mean that we're making a great leap of angle at least pi over 2. And now we know that these angles are actually going to 0. So it's not possible. Which is fantastic, because that means, so combining this condition asterisk and double asterisk, by asterisk and double asterisk, each quadrant is visited infinitely many times. And in particular, so each quadrant is visited infinitely many times. So there will be infinitely many terms with positive imaginary part and infinitely many with negative imaginary part. So there must be an infinite number of k, of integers k, such that the argument of 1 plus I, 2 plus I, and so on, n plus I is negative, and likewise an infinitely many case such that the argument, sorry, not the argument, but the imaginary part, such that the imaginary part, our product, is greater than 0. And that is what we want. That closes our proof. A very nice geometric proof. A lot of geometry behind it. And to be honest, I enjoy these types of problems very, very much. Combining facts from geometry, complex numbers, mathematical analysis, calculus. Truly beautiful. And that's it. I hope that you've enjoyed this video as much as I do, and I will see you next time. Goodbye.